Hey there, AP. Let's get started going over some of these questions that we've got from this particular worksheet, some good practice. So here we go. Number one, as you can see, you've got something on an inclined plane. The angle is given, and since friction is not mentioned, we're going to assume there isn't any. All right, so an inclined plane, as I've mentioned previously, inclined planes are interesting because you have your free body diagram. Okay, this is my first shot with the old smartboard. I guess I have to be careful how I draw. All right, so gravity is going straight down, right? And then we have a normal force, which should be perpendicular to my surface. And then I'm going to have tension along the rope. And like I said, I'm going to ignore friction. So one of the main things that I do when I'm working with this sort of a thing is I'm going to consider which way would this block accelerate if that rope were cut. And if the rope were cut, it would go this way, wouldn't it? So what I'm going to do is consider the Cartesian plane to be along the area of motion. So if I tilt that in my head, I tilt it to the right, what I would notice is that the normal force and the tension force would be, in that XY coordinate system, but the FG would be a little bit whacked and, sideways. So when we have something that's diagonal, what we do is we're going to break it up. We're going to break it up into left and right, up and down sorts of vectors. So I'm going to make what I call the triangle within the triangle. Okay, because of geometry, this is still a 35-degree angle right there. And this one, being the opposite side, is going to be FG sine of theta. And this is going to be FG cosine of theta. Now, when I look at things that are balanced, I'm dealing with balanced forces or something that's not accelerating, something that's not changing its velocity. The way I like to look at these is that everything pointing to the left has to equal everything pointing to the right. Everything going up has to equal everything going down. Now, a fancy way of saying this on the AP exam, what they tend to say is that the sum of the forces equals 0. But I like this. This doesn't really matter. It's totally up to you how you want to go about it. All right, so my next one, here's what I'm going to do now. Let's work with left and right. Okay, now when I say left and right, I'm talking about the x plane. So everything that is trying to go down the hill, all right, well, that's FG sine theta. And what's trying to go up the hill? Tension. So those two have to be equal and opposite to each other. Okay? And actually, that is exactly what the question is asking for. But to continue, what I would also set equal up and down, I would say that the normal force is equal to Fg cosine of theta. Because as you can see, these two are equal and opposite of each other when you're looking at those two arrows. Okay? Now, I don't need these for this particular problem, but I am going to work with this one. Now, considering that I know that the mass, Fg, is really mg, so mg sine of theta equals tension. The mass is 34.5. This is 9.81 meters per second squared. Sine of 35 degrees, and that's going to be 194 newtons, give or take. All right, we don't really worry too much about the sig figs. 3 will do the trick. All right, so there's that particular question. Let's move on to our next one. Find the tension in each cable supporting the 600 Newton cat burglar. All right, now the first thing I want you to notice is this, that it's given to you in newtons, not in kilograms. So that's really helpful. That means that this, we already know it. It's 600 newtons. I don't have to do anything fancy there. All right, my other tensions, I'm going to have one tension going this way. Let's call that T1. I'm going to have this tension going this way, and I'm going to call that T2. Now, thanks to wonderful old geometry, since, let's face it, this is my sideways vector, Okay, I can break that up into left and right thanks to alternate interior angles. That's going to be 37 degrees. All right, so I'm going to call this T1x. I'm going to call this T1y. And then I'm going to take a look at what I can do with that. Okay, I want to know the value of T1 and T2. That is the point of the question. Okay, so if I work with the premise of forces up equal to forces down, what's pointing up? T1y, and I mean like straight up. That's T1y. And what's pointing down? Fg. So this tells me that T1y has to equal 600 newtons. They got to be the same, right? If that's the same, and I now know, let's face it, if I know some of this triangle here, right, this is going to be 600 newtons, and I'm looking for this one. Well, that's a pretty straightforward trig thing going on right there, right? We've got an opposite side and we've got a hypotenuse. So you can use the sine function, opposite over hypotenuse, sorry, not T1y, that's my bad, just T1. That looks like the same fraction, like little line in there, but whatever, you get the idea. T1 then is going to equal 600 newtons divided by the sine of 37. And, let's see. I get 997 newtons. Remember to stay in degrees, not radians. Okay, since we still have the same triangle here, what we can do is now find this piece right here. We can find this one using the cosine function. So let's do that. And the reason I want to do that is because if I look at left and right, and you look at what's pointing left, that's T2. What's pointing right, T1x. If this isn't going anywhere, those two have to be equal to each other. So considering what I know, and you can use tangent, you can use cosine, it doesn't really matter to me what you want to do. So in any case, let's figure out T1x. T1x equals, all right, let's use cosine. The cosine of 37 equals Tx over, what did I figure out that was? 997. And so I can multiply these two together, and I'm going to get Tx equals 796 newtons. So there's my second answer. Oh, sorry, not Tx. Tx is 796. Sorry, let me just finish. That is the same as T2. Okay, so there we go. T1, T2. Finished. Let's look at our next one. Okay, this one's kind of interesting because we are looking at our first friction problem. We also have something that's on a flat plane, but it's being pulled at an angle. And that's a little bit, I like these. I think these are kind of fun. All right, there's going to be some triangles in there, but we also have some stuff that's just on a flat plane. So, free body diagram. All right, so there's my tension. And you can see it's 875 newtons. All right, here's Fg, which is going to be mg, normal force, friction force. Well, they say kinetic friction. You could put an F sub F, or you could use F sub K. It doesn't really matter. All right, so you've got those. This is your free body diagram. Now remember, if you're doing a free body diagram, you do not put component vectors in there. So the ones I'm going to draw next do not go on an official free body diagram. These are just my working diagram right here. So when you're taking the AP exam and they ask you, to draw a free body diagram, you are never going to put these red ones in there, okay? They're going to actually have a separate spot for you to write it, but just remember that. Now, we're given a 250 kilogram crate. It's being pulled across the floor at constant speed. Right there, that's a huge clue to us. That tells us that we're dealing with static, or we're dealing with balanced forces, right? So when I say balanced forces, what I mean again is that the left is going to be equal to the right, which tells me everything pointing left, which is friction, is going to be equal to Tx. And if I do all the forces going up equal all the forces going down, again, let's look. What's going pointing up? I've got two. I've got normal and I've got Ty. And pointing down, I have Fg. So this lets me know, this is an important piece right here, because you can't just set the friction equal to, or I'm sorry, you just can't set the normal force equal to the gravitational force. It's not true. All right, you have a second arrow pointing up. So when we get going with that, that is going to be an important thing for us. Okay, so let's do some calculating, shall we? Let's first figure out Fg. So Fg is going to be 250 kilograms times 9.81 meters per second squared. And when I find that, I get 2453 newtons. All right, then I'm going to work with my tensions because I know that. All right, so I'm going to use a little sine and cosine action going on there. All right, so if I want to find Tx, Tx is going to be T cosine of 22, so 875 cosine of 22, that's going to be equal to 811 newtons. So this one is 811 newtons. That tells me right away that this has to be 811 newtons because these two are the same. And the reason I want to know that is because I'm looking for mu, and mu is going to be friction over normal. So I now have half of that done. So that's 811 over. All right, so our next step is going to be to find the normal force. If I'm going to find the normal force, then I'm going to need to know Ty. So Ty is going to be T sine of 22. So 875 sine of 22. And that's going to be 328 newtons when I do the math there. So now I'm going to use this formula right here that I came up with, and I'm going to find the normal force. So I'm going to go back to red so that you can follow me down there. All right, so normal force is going to be equal to Fg minus Ty. Now remember, this is something we came up with based off of this. There are no hard and fast rules for exactly what's equal to what, except with up equals down and left equals right when we're dealing with a constant speed. Everything else you have to do on an individual basis. So don't try memorizing a whole bunch of junk. It's not going to help you, with the exception of just knowing how to find gravity and how to find things like coefficient of friction and stuff like that. All right, so we've got, where did I put gravity? Oh, there you are. All right, 2453, and we're going to take away Ty, which is 328. So for normal force, you get 2125 newtons. So that's going to go right there. And when you do the math, you get 0.382. Remember, the newtons cancel. Mu is one of the few numbers we have in physics without any units on them. All right, so there's that one. Now this one is tricky. All right, part of why it's tricky is because you have three bodies that you have to account for. What's also tricky is that you're not being given any values and you are asked to find a whole bunch of things with just variables. So our favorite, no numbers at all. All right, so the way this is designed in this question, this looks exactly like you would see it on an AP exam where it's like just do the forces. So free body diagram on M1, no components. Gravity is always going straight down. Actually, if you're smart, you're not even going to write gravity. You're going to do, actually, let me just erase that. Let's just start over. All right, we'll put gravity down there, but instead call it M1G. And the reason that you should really do it that way is because, let's face it, you've got M2, and then you've got this capital M, which is ridiculous. They should just call it M3 or something like that, but we'll do our best. All right, normal force, because you're going perpendicular to your surface. And we've got a tension. I'm going to call it T1 because it's attached to the first block. And then it mentions a frictional force of F. So just leave it as a lowercase f. It's going up the incline. And the reason I know that is because, let's face it, M is a capital letter, which is supposed to signify to me that it's larger than these other guys. So if friction wasn't, the way that this wants to move, So the way that this wants to move, this larger mass wants to pull it downward. All right, we're going to be doing some friction. We're going up the incline here with our friction. So let's continue. All right, so there we go. We've got our free body diagram right there. You know what? Okay, let's change that explanation because that was a terrible explanation. All right, so let's consider if you did not have friction trying to go up the incline, the blocks would be sliding down. We're going to assume that we're going to say that our friction is going up the incline here. I'm going to double check this one a little bit later, but I'm almost 100% certain on the friction is going up the incline. So there we go. There's our free body diagram for that one. That's all we have to do. Let's go to the next page. Okay, determine the coefficient of kinetic friction between the inclined plane and block number 1. Alrighty, so I'm going to redraw this free body diagram that I had going on here, and then I'm going to start breaking things up. So this is M1. I've got M1G going this way, normal force going this way, friction, tension number 1. Okay, now coefficient of kinetic friction between the inclined plane and block number 1. First thing I'm going to do, I'm going to break this up into my triangle within the triangle. This is theta. This is going to be M1G cosine of theta because it's the adjacent side, M1G sine of theta because it's the opposite side. This is why it's going to help me eventually. Don't put FG because you're going to have another FG on block M2. You're going to have another FG on block capital M. So be specific. It'll make life easier. All right, so we want to know the kinetic friction, the coefficient of kinetic friction between the inclined plane and block number 1. All right, so the normal force has to be equal to this. All right, if we go with up equals down, forces up equal forces down. Again, we're tilting the coordinate plane here so that we have a real up and down. All right, but normal force is equal to M1G cosine of theta. Okay, the friction is just equal to F. So to do mu, it's actually not that bad. You just say F divided by M1G cosine of theta. Now the tricky part to these questions when you're leaving them in the following terms is you got to know what terms you're leaving them in. All right, so that satisfies what we're doing here. That's not so bad. Okay, now next, let's move on to this next one. Determine the value of spent black mass M that allows blocks 1 and 2 to move with constant velocity down the plane. Now this is where things are going to get crazy a little bit. We're going to work with a system of equations. Okay, so I think I'm going to mark up over here. Let's go back here. M1G normal. Oh, you know why? Because look where the velocity is. That's why my friction's going up the plane. I just totally missed that in the diagram. Okay, let me erase that and make that easier to see. Let me just start over. Alrighty, M1G normal force T1 and little f. All right, we've got these guys, M1G sine of theta. Oh, I'm going to run out of room. I'm just going to draw an arrow. M1G cosine of theta. All right, since we've got those, we'll be good there. Now, let's take a look at the other blocks. We've got the same sort of thing going on here. All right, M2G, Fn, actually we'll call that Fn2, we'll call that Fn1, and then T2, 2F, gosh, I'm almost off the page. All right, and then let's break that one down. Mg2 sine of theta, M2 mg2 sine or cosine. All right, hopefully that's almost legible. Sorry. You know what? Let's see if I can erase that carefully. Lost my whole triangle there. Let's try that again. Let's try that again. M2G M2 G sine theta. And then, you know what? I'll just redraw the other one later. So M2G cosine of theta. All right, so that's the second one. The third free body diagram that you need is for the hanging mass. I'm going to put it here. Mg, big M, little g, is your downward force. Your upward force is going to be tension number 2. And it's the same rope. It's going around the pulley, which we're ignoring completely. You'll thank me later when we stop ignoring the pulley. But really, it's the same rope, so it's just changing the direction of the tension. All right, so you've got 3 objects with 3 free body diagrams, and so what you need to do is to work with all of them and make a system of equations. And it's rather elegant what tends to happen. All right, so I'm going to start with the hanging mass. Let's do it. I'm going to start all the way back over here. All right, so we know that these forces are balanced, right? We want to move with a constant velocity down the plane. So this means that big M, little g, has to be equal to T2, right? Because you've got balanced forces, constant velocity going down the plane. Now let's look at the next block. All right, so when we are looking at M2, it's trying to pull it up the hill. 2F is the friction trying to go up the hill, plus T2 is trying to go up the hill. All right, I just want to line these up a little bit better. Let me just rewrite this so I can line it up a little bit better for you. Just move that over. That way we can keep the equal signs together, right? That'll be easier to see. So 2F plus T2 is trying to go up the hill. And for block 2, what's trying to go down the hill, right? That's the main thing that you have to ask yourself. Well, for block number 2, you've got mg2 sine theta. I think I said that backwards, but you get the gist, right? And there's also T1. T1, I think I forgot to put on there, right? But this guy over here's got T1 trying to go down the hill. There we go. Now my third one is for block number 3, which is, well, actually it's block number 1, sorry. It's the first one over here that we started with. So you want to look at your free body diagram and ask yourself, what is trying to go up the hill and what is trying to go down the hill? What's trying to go up the hill is T1, and then the friction. And what's trying to go down the hill is M1G sine theta. Okay, so what you end up with are 3 equations. And watch this magic that happens, right? If we add the equations together, that drops out. That drops out, right? Because they're pulling in 2 directions for different things, so they cancel each other out, and we can just add these together. So we get 3F plus big M little g equals M2G sine theta plus M1G sine of theta. All right, so it simplifies really nicely. Now we are trying to find M. So let's move things around, right? I can actually also take the g sine theta out of the right side of the equation because it's common to both, right? That's pretty standard stuff. So if we say g sine theta m2 plus m1, and then we move over the 3f, so let's subtract that to this side. That'll equal big M little g, and we can divide both sides by g. So I can get g sine theta m2 plus m1 minus 3f all over little g. And it's totally up to you if you want to take the g out, cancel it on the left, and then just have sine theta m2 plus m1 and then minus 3f on g. Like move your fraction so just these guys are on a fraction together. Either one's acceptable. All right, but that is actually, that's your answer right there, this big colossal monstrosity. That's your answer. You're going to see a lot of them like this. All right, but here's the trick. Take each block, each object you're working with, do a free body diagram for each one, and then set up your statement for each individual object, and then add them together. Different things will cancel out. They have to. And then simplify. Simplify as best you can. All right. That is this particular practice. Thanks for following along.